Good afternoon and welcome to this talk, which is part of the Kotak Center's Distinguished Lecture Series. We are delighted to have as our guest speaker for today's seminar a legend in the machine learning field, Professor Tom Dietterich, who is currently Distinguished Professor Emeritus at Oregon State University. So Tom received his undergraduate degree from Oberlin College in Ohio. Then he went to the University of Illinois at Urbana-Champaign, where he got his master's. Got fed up of the snow and the cold, went down to Stanford in California, and then received his PhD in 1984. So immediately after that, he moved to Oregon State University, and over the next 3 decades, he's built up one of the strongest machine learning groups in the world. And he was the prime mover in getting this department to have a completely new face of in the AI and ML world. So Tom is, as I said, one of the pioneers of machine learning. And just to give you a few examples of that, he was the co-founder of the Journal for Machine Learning Research, JMLR, which most of our computer science faculty would kill to get their papers into the journal. So maybe with Tom's help, they'll get a few more of them now. But that's not the most prestigious, one of the most prestigious journals in the world. And even when AI was in its winter stage, he was the Triple AI chair in 1990 and the Emeritus chair in 2000. So you can see that Tom has had essentially been in the vanguard of machine learning and propelled the field forwards. This year, he was the proud recipient of the 2025 Feigenbaum Award for Applied AI Research. Last year, he also got the Ichikai Award for Research Excellence. He's also received many service awards. He's also currently the editor-in-chief, so to speak, of the archive. So Tom has been one of the people who have had a very large footprint on computing science in general and machine learning in particular. So in today's talk, he'll tell us how can you take AI, which is normally considered to be unsafe, and actually make it safe. So with that brief introduction, let me request Tom to present.
Thank you. Well, thank you for that very, very kind introduction. So the talk that I'm giving today is really the result, at this stage in my career, I'm asked to be on various study panels where we're supposed to come up with answers to difficult questions. And last year, the US National Academy of Sciences had a study panel on machine learning for safety critical applications. And so this gave me an opportunity to learn something about safety engineering, which I hadn't studied, because most computer scientists don't study safety engineering, and that probably shows in some of the reliability of our systems. And so this is a reflection of what I learned spending time with the safety engineers. So the talk will be in 3 parts. The first part will really be half of the talk, which is how does machine learning methodology and maybe technology need to change so that we can apply it in safety critical applications. The second part will then be to say that, in part 1, we're looking at traditional safety engineering, which assumes that we know all of the hazards that we need to design against. But of course, the real world is an open world, and there are typically unknown hazards that will be discovered during system operation. And so part 2 is adopting Nancy Levison's view of safety as a control problem. That is, we have to defend the safety of our system against disturbances that are going to push it into unsafe operation. And then part 3 is a reflection on the need, an AI view on the need to be able to do system redesign frequently in order to adapt to new problems that we discover. So how does traditional safety engineering work? And this is my approximation. I could have put up V diagrams and W diagrams, but I went with a bulleted list. And I've been, as an example, I'm going to use the automated driving for semi-trucks on freeways. There's a startup company in Toronto led by Raquel Urtasun, who is a very good computer vision researcher. And they are trying to use this as their business case. She had previously run the Uber self-driving lab, and she has affiliated with the University of Toronto. So in traditional safety engineering, the key idea is to define something that's called the operational domain. So we define the intended scope of the system, and then we design a state space, which is the domain in which the system will operate. And the idea is that we want to give a guarantee that as long as the system, well, the guarantee that the system stays in that domain and is safe when it is in that domain. And so then typically we need to break that down into scenarios. And so a very important concept is scenario-based design. We break down the scenarios and then we do a hazard analysis of each scenario. So we might think about, in the self-driving case, a situation in which someone cuts in front of us from the left side of the vehicle, and what are the hazards? Well, we might collide with them. Someone might collide with us from behind, and so on and so forth. And then what are the harms that could occur, which are very clear in these cases, things like death and severe injury and damage to infrastructure. And then we try to do a risk assessment. Now, in most of the traditional safety engineering applications, the main hazards are caused by equipment failure. A cable breaks, a vacuum line breaks, something like this. And so it's possible to estimate the likelihood of these failures if we can model the lifetimes, right? So we do some sort of lifetime survival analysis to build lifetime curves and estimate probabilities. And so we can come up with a measure of risk, which is a combination of probability of an event and the severity of the event. And then safety engineers insist that there is no such thing as a 100% safe system, that instead you have to ask, well, what does society consider is an acceptable level of risk? I guess the pointer isn't working, but if we compare, for instance, safety on railroads to safety on highways, we are much less tolerant of problems on the railroad than we are with highway. We accept tens of thousands of deaths in the United States on highways, but if that happened in commercial air traffic, that would be a national uproar. And of course, one interesting phenomenon might be that if we really can bring more automation to driving, our expectations for what is an acceptable amount of deaths will go down. So we're going to make the problem more difficult for ourselves to the extent that we succeed in safety engineering. So then in the traditional, I think an interesting problem for us when we think about these kind of driving scenarios is that a lot of the risks don't come from the failure of our system components, but from the behavior of other drivers, pedestrians, cows, whatever might be on the road. And so this risk assessment is much more difficult and depends also to a large extent on our controllers that we've built for the system. So the order may need to change depending on the system. So you may need to have done quite a bit of the design before you can do the final risk assessment. But in any case, coming out of the risk assessment, we need to say, well, to achieve, what did I say here, 1 death in 10 to the power 8 hours of operation, we need to introduce some kinds of mitigations in our design process. We might need to add redundancy, redundant braking systems, redundant power systems, and so on, in order to get down to that level of safety. We may need to identify some sort of a fallback condition. For self-driving cars, they usually want to have the vehicle slow down and pull over to the side of the road. That's not always a guaranteed safe state, but of course, removing energy from the system is generally a good idea. So maybe it's not too bad. Yes?
You define this in terms of acceptable in hours. It could also have been in distance, right?
Yes, many different, right. So miles traveled would make a lot of sense. I think for airlines, they do it in terms of hours of operation, though. That's what I've also seen for the cars, at least in the U.S. So the mitigations might be, that we introduce some kind of feed-forward control so that we are guaranteeing a certain safe distance. We may need, when someone overtakes us, maybe we decelerate or change lanes. So we change our controller to try to make things safer. But in any case, coming out of this analysis, we try to identify the safety requirements. So of course we have functional requirements for the system, We may also have non-functional requirements that have to do with cost and weight and things, but then we have our safety requirements. And so ideally, coming out of these requirements analysis, we should then be defining our tests, right, and our verification procedures. This is one of the principles of safety engineering, is that you really want it's similar to in machine learning where we want an independent test set. You'd really like to have an independent sub-team who's responsible for verification and validation, writing the tests, and so on. But then having gotten all of our requirements together and decomposed the system to the point that we can give our safety specifications for each subsystem, then we can design and develop the system to meet those requirements. This may involve, the safety requirements may involve things like the accuracy of our perceptual subsystem, of our braking system, and so on. And then having done that, we then want to verify that the system meets the requirements. The literature tends to break this up into verification, meaning that we met the requirements that we wrote down, and validation, which is checking that the requirements we wrote down actually were valid, right, that they describe the world we want. And so I don't know what the terminology is in general, but this is what I've seen, is that validation is more about, did we do our requirements analysis correctly, so we built a system that's actually going to meet the customer's needs. When we then deploy the system, we have to worry about maintenance and monitoring. So the system this bleeds into the next part of the talk about what happens after deployment. And of course, in some domains, like in aeronautics, we have to produce a large set of documents to satisfy regulatory certification of the system. So this is, possibly a little scrambled, but is the traditional safety engineering process. So now what happens when we go to machine learning? Well, for the last 25 years, machine learning and data mining people, we've been going to industry and saying, you have collected all this data as a side effect of your business. You have transaction histories, you have medical records. We can mine that data and give you insights that give you business value, actionable insights, right? We've been telling them for this. And this is part of the general machine learning idea that we use data that's already been collected for some other purpose. So if we think about the famous ImageNet collection benchmark for computer vision, the images were all shared by people on photo sharing sites. They weren't collected to build a good computer vision system. And the pile is a big collection of 800 gigabytes of data that's used to train large language models. And this includes things like scientific literature, all of archive. I think there's all of Stack Exchange, Wikipedia, things like this. So this is the current practice in machine learning, is generally that we're training on data that was collected for some other reason. And so the consequences of this methodology is we have no guarantee that the training data covers the operational domain that the system is expected to operate in. We have no guarantee that the machine learning system will learn a model that meets the safety requirements. Unfortunately, we have a lovely and elegant statistical theory of machine learning, but it only gives us statistical guarantees if the data at deployment time is the same, it comes from the same distribution as the data that we trained on. Well, this data doesn't come from any distribution that would correspond to a deployment distribution necessarily, right? So we can't use these statistical guarantees. And I think a further note is that from statistical guarantees alone, it's hard to imagine you could ever get more than maybe 2 nines, right? I mean, most computer vision systems are not even 99% correct. And to imagine that you could get, say, 5 nines or 6 nines of accuracy in a machine learning system is really, really hard to consider. So I think we need a new methodology for building machine learning systems. And to a large extent, I think we need to have more of a scenario-driven process of collecting our data. So I think our goal should be distribution-independent accuracy guarantees for machine learning. So I want to deliberately collect our training data to make sure that we're getting very good coverage of the operational domain. We may actually also need to cover regions around the operational domain, because one of the things that a system may need is to detect when it's in the operational domain. So for example, for the highway driving case, maybe the operational domain is when the roads are dry, there's no fog. So we would need a system that can give an answer to that and say, if it's foggy or the roads are wet, then the vehicle is just going to wait until conditions have changed. So in any case, if you look at what's happening inside companies like Wabi and Waymo, they have adopted risk-driven sampling techniques that I'll describe in a moment. And then I think the other thing we need to do is to be able to verify the approximation quality of the learned model. So I would like to see formal methods brought into machine learning. And this is a big ask, but there's a very small community of people that have started to look at this. And it could be that during the verification process, we actually need to collect more data and train the model on that as well until we get one that we can verify has learned a good function. So when I talk about sort of risk-driven sampling, this is what I mean. Most of the companies have adopted a methodology where they first go and collect real-world data. So for the driving case, they collect thousands of hours of driving on highways, and then they use that to build and validate a simulation model of what driving is like. Sometimes they call this a digital twin. I think that phrase is more aspirational than real, but the idea is that we want to be able to simulate situations that we are not encountering in our training data. In particular, we don't want to deliberately cause accidents in order to collect data on what accidents look like, collisions, crashes, and so on. But we need a way of simulating them. So of course we can take this real world data, which will tell us things about how other drivers behave and so on. Combine that with very good physics simulations that we have now to simulate the physics of the vehicles and so on the road. So then what they do is they adopt this Bayesian optimization or surrogate model optimization strategy. So the idea is to fit a surrogate model, so we can fit a machine learning model to the data, but it's usually too difficult to get from the machine learned model estimates of what's called the epistemic uncertainty, right? So that is lack of knowledge uncertainty. So if we come over here and look at this plot, right? Suppose that the true function we're trying to fit is the dashed line here, and the blue line is an approximation to it that we have fit to our data. What we want are these error bars here, which say how uncertain the model is, and people particularly like the Gaussian process model because it gives you an explicit. It is Gaussians are wonderful, right? And in particular, it is a closed form solution to the Bayesian inference problem of inferring how uncertain we are about the true function. And so once we fit that, we then use what's called an acquisition function that tries to sample new points in regions of high uncertainty. Or we can also actually formulate it to be more adversarial. Try to sample points that will break the current controller that we've been training. Try to sample points that will cause collisions, this kind of thing. So the idea is that then we can, once we've generated these cases, we can then simulate them and use that as new training data, update our machine learning model, update our surrogate model, and repeat until we're not able to find any more bad cases. And so usually this acquisition function, I've described it as primarily adversarial or uncertainty-based, but usually we're interested in attaining reasonable coverage of the entire state space and very good coverage of the hazardous regions. So we usually talk about hazardous states being in the sort of backward reachable set of states that if we enter them with high probability, that will lead to a harm of some kind. So we want to stay out of those risky regions. So we'd really like to learn where the boundaries of those are because we want to have some safety margin beyond those.
Question.
Yes.
This is some sort of function regression. How does this connect with the simulation exactly?
Well, so let's say that the function we're fitting is actually the obstacle detector for the vehicle, and so it's actually outputting sort of a region of the image that contains an obstacle. So then we would want. I'll show an example of them using it in a second, but the idea is we will use this to generate an input state of the world that will lead the current controller to fail, and so then we will have to figure out. I'm skipping a lot of steps, aren't I? On how to turn that into an example of what we should have done instead, and then train on that. Yeah. Yes.
So this dotted line, I presume, is what you learn from your ML machine.
Well, no. That would be the true function that we're trying to learn. The ML function isn't really here, only the surrogate.
So I wanted to know, is the ML, like the regression learned through ML, would that be used in some way to generate this dark blue line, or that is not used at all?
In an ideal world, we would actually get this epistemic uncertainty estimate out of the model itself. But in most cases, those models are these gigantic neural networks, and we don't know how to get good epistemic uncertainty estimates out of them. So instead, we fit this Gaussian process approximation. Often, we're not looking at the raw image. Usually, we'll be using one of the latent spaces in the neural network as the space here. Or I'll talk about using a kind of configuration and trajectory space in the physical world. That's the space we want to be operating in. So here's an example of work on this. This was from now 2 years ago from Wabi. Wang et al. Published this work on what they call AdVsim, which generates adversarial scenarios. So they collect data for vehicles driving around, and their data looks like this. This is what they call the ego vehicle. It's the vehicle that we're trying to control. This was a bus, and these black things are pedestrians, and we're seeing a sort of time series of how they all moved. So the bus was stationary. The ego vehicle was stationary, I think, yes. It doesn't come out. I think it was slowly inching forward, but it doesn't render very well here. And here's a pedestrian crossing the street, and here's some other pedestrians going this way. Okay, so in this scenario, the pedestrian makes it all the way across the street safely. But now what they've done is they fit this surrogate model, and they're operating in a fairly high-level space where they have the location and trajectory of each of these vehicles and pedestrians and so on. If there were dogs or whatever, they would have them too. And as well as street signs. I think this is a street sign or a traffic signal or something. And so that's that. And they have the LiDAR data. They're very focused on using LiDAR, so the sense data is point clouds. And then what they do is this. What this adversarial algorithm does is it tries to select one or more vehicles and perturb their behavior in order to maximize the probability that the system will cause a harm, a collision of some kind. So they have this adversarial loss function they're trying to maximize. And so this is one of the scenarios that gets generated. In this scenario, the bus is moved to this lane and it drives away. And what happens is it turns out the controller was holding this car still because the bus was in the way. But now that the bus is not present, the car moves forward and strikes the pedestrian. And so we have the collision. And so this is the idea, is that we need to search in the space of these configurations of vehicles and pedestrians and their trajectories to try to maximize the probability of a collision. And so they actually will generate n different adversarial scenarios for this starting state. So n different attempts to cause a collision, and then choose the one that gets the largest adversarial loss. And they'll do that for a whole set of original scenarios. And then this gives them a collection of new examples that they then will need to run run their planning system on to figure out what they should have done instead. So in the paper, they report that looking at the scenarios that are generated by this adversarial scenario generator, they greatly increase the number of collisions. Instead of having 8 collisions, we're up to 32 or something like this. So more than a 300% increase in collisions, which is fantastic, right? They're part of their other, harms are they don't want to bounce the passengers in the vehicle around. So they have a comfort score for lateral and for jerk of the passengers. And there's very slight changes. There was a slight increase in badness here and no change there. It's interesting that that this adversarial approach also uncovers some perception failures. So this is the F1 score for spatial occupancy, and you can see that it drops slightly in these adversarial situations. And this was their score for predicting the future position of the other vehicles and pedestrians, and their accuracy went down there slightly also.
Question?
Yes?
So these were in simulated scenarios?
This is all simulated, right?
Okay.
Yeah. Yes, they don't want to actually strike pedestrians down. I mean, it's estimated that if you just wanted, if you had no way of enriching the data with these bad cases, you would have to collect something like 9 billion hours of driving to have enough data covering these corner cases. So that's why Waymo also has made this commitment to simulation. In their papers, they don't talk about how they validate the quality of the simulator. I would like to see that, because I'm not sure that that's a whole lot easier than the original problem. But I guess certainly the physics part of the simulator is something we can trust. But the models of the behavior of the pedestrians, I mean, they're modeling them as these little time series, right, of positions. But are they capturing, I don't know, a more cultural or ethical kinds of behaviors? I mean, someone was describing to me the following scenario. So the car is driving down the road, and over on the right sidewalk, a man collapses, like an elderly man just collapses on the ground. A woman on this side of the street sees that. Now, what should the car do? We know that woman is maybe going to cross the street to try to help out the person who just fell. So the car better stop. But we're bringing a lot of human and cultural knowledge to the situation that I think exceeds the knowledge that this system has, because it's unlikely that that's part of their simulator. So I think there are a lot of things that this still doesn't capture.
Machine learning, you don't want to overfit the data.
Right.
It looks like, whenever there is uncertainty, you collect more data and you
Right.
make sure that it fits very well. So is that correct interpretation of what you're saying?
Right. In some sense, we're assuming that we have access to an oracle, and so we can draw enough data until we have, so we're always going to fit the data, I think. Perfect.
Overfit it as much as possible.
Well, is it overfitting or just fitting? I don't know. Yeah. It's an interesting discussion we can have. Okay, so then they say, what if we train on these data plus the adversarial cases, then we can reduce the number of collisions. So they're able to improve performance on these collisions. It's still a rather large number, 17%, but that's less than 33%. But they don't report in the paper what happens if they iterate this many, many times. Can they eventually get the predicted collisions down to a very low number? I think the most important thing to notice here is that this is operating at a kind of semantic level, at the level of trajectories and agent behavior. The first attempts that people did in this area were trying to operate on the pixels of the image, or the pixels in the point cloud, and that was pretty much a total failure, because for one thing, a 10 gigapixel image has 10 billion dimensions to it, or actually 30 if you count R, G, and B as separate. And so search in that space is just impossible. But the other thing to notice is that because they're not working in the image space, but their sensors are working in the image space, they need to have a very high fidelity simulator of what the point cloud will look like. When they move the bus over there, now what does the point cloud look like? They have to simulate that very well. So that's one thing is risk-driven generation of training data, so that we oversample the parts of the space that are very important. But then there's always a worry with machine learning. The data live in this very high dimensional space. How do we have confidence on how the fitted function, what its behavior is? Here's a very simple one-dimensional case. Imagine that these orange dots are the training examples, and the blue curve is what the neural network fit to the data. And I make it sort of this jagged piecewise curve because if you're using ReLU transfer units, you're fitting a piecewise linear function to the data. So this is roughly what it looks like. So of course, we have no explicit specification of correct behavior aside from the data that we've collected, which is it's both the benefit of machine learning is the specification is the data, but it's also the problem that it's an incomplete specification because it only tells us how the function should behave at each of those orange dots. So what we're worried about is that it could be that somewhere between the training data, the function does something crazy, right? How do we gain confidence that that's not happening? So one idea would be to try to bring some formal methods to prove a bound on the difference between the blue curve and, say, a linear interpolation of the data. So, in one dimension, it looks very plausible. And there's actually some published work by Singh et al. Where they show how to do this for over a convex region of the space. They can bound the maximum between f of alpha x1 plus 1 minus alpha x2. That's the blue curve, right? For alpha varying between 0 and 1, and the orange curve is alpha of x. The convex combination of the value of the function at these 2 points. And so we want to find the value of alpha that maximizes that difference, and hopefully we will discover this gap. And if this is large, then what we probably want to do is draw a new sample at that point. So the big challenge, of course, with these formal methods is, can we scale them up to the practical size of real neural networks? I believe in the papers that they've done, they were using this for a different purpose. So I'm kind of repurposing their algorithm. But they can handle small computer vision problems, sort of the CFAR scale. But I don't know, whether we can really scale them up to these large problems. So I think it's an open question. But people have been making progress over the last 5 years in building better and better reasoners for reasoning about these networks. And there may be something we can do on the machine learning side, like could we learn an over and under approximations of the blue curve that were easier to prove properties of, some kind of surrogates. Another approach, there are people that try to design neural networks that have guaranteed Lipschitz constants so that we know that they're smooth in some sense, and that may be another approach. But in any case, we want some sort of guarantee that there's no crazy behavior in between the data points. But as I say, this looks great in one dimension, but I think we would need to be doing this interpolation in the semantically good space, such as what the adversarial people were doing, right? So my thought would be, or my proposal is, for each training case, can we find our k nearest neighbors, where we choose k to be basically the number of parameters that are in the scenario. So maybe that's something like 60 or 100 dimensions. And then we can consider the all convex combinations of those k plus 1 points and look for the maximum discrepancy in that region. And that, I think, is something that would be feasible. In fact, it may be more feasible than some of the things that they've been trying to do in computer vision, because it's a much lower dimensional space. Okay, we can also use this for verification-based active learning. As I was just hinting, if we can find the value of alpha that maximizes the discrepancy, then we could sample a new scenario at that point and collect a new response value, YQ, train the network on it, and maybe we can repeat this until we can't find any failure regions. Okay, so that gives us, if this dream can come true, that gives us a machine learning model that it fits well independent of whatever the test distribution will be, because it's well behaved throughout the space. But now recall that our criterion for harm was something like under ordinary operating conditions, the probability of a failure is less than 1 in 10 to the power 8. And so how can we achieve that? How can we estimate that? We have built an extremely skewed probability distribution to train our model. We need to go back and somehow model the original distribution. So one solution is to build a probabilistic model of normal operations. And so we could estimate the probability of the initial states, the probability of the system behavior, the probability of the behaviors of the other agents, and that would give us, and that would be quite a challenging modeling problem. But assuming we could do that, then the idea is to use importance sampling to, because of what our training data was drawn from is this Q of S distribution, which greatly exaggerates the probabilities of failures. We saw that we were having something like collisions in 37% of the cases. And so then we want to do our simulations according to this distribution Q of S, and then reweight them. For each failure, we downweight it by that ratio P of S divided by Q of S. And so there's an example of this. Michael Kolkendorfer, who's a researcher at Stanford University, faculty member there, has done a lot of work in aviation safety. In fact, he has a startup company also in autonomous aircraft. And he applies the same surrogate model approach to trying to do this, sort of separately from training the model, just to evaluate the model. And so his task is runway detection. So imagine an aircraft that's trying to land in this airport. It needs to detect where the runway is visually and then land on it. And using importance sampling, they're able to estimate that the probability of failure is about 5.8 times 10 to the minus 3, which still sounds a little high to me, but they can do that with roughly 500 samples, I would guess about here. Whereas if you just drew Monte Carlo samples, 1,000 Monte Carlo samples, you would only get 6 out of 1,000 would actually be failures, whereas 57% of these samples were failures. So we can get a better estimate using importance sampling than we could by just doing simple Monte Carlo samples from the original distribution P of X. So I think with these tools, if we could do these things, then I think machine learning could be integrated into the standard safety engineering process, right? Because we've been able to address the problem of designing a system that contains machine learning, but that could meet the requirements, and we could then verify that formally. And we can then estimate the risks of the system. But I was talking to Michael 2 weeks ago. I was visiting Stanford, and he's got a new book coming out called Algorithms for Validation. And validation for him means everything in verification and validation. And he says no single validation method is sufficient. He was responsible for the collision avoidance system that is being deployed commercially in the United States for aircraft. And he spent 5 years and a whole raft of different validation techniques to validate the solution that was found there. He was actually solving a partially observable Markov decision process, because each aircraft kind of has to reason about whether the other aircraft is functioning properly. Is the pilot even alive? All kinds of things there that are invisible. And proving that it covered all possible eventualities was quite a challenge. He couldn't do a formal proof for the whole system, so he had to be able to prove subsystems and simulate and test others, and so on. Okay, so that's great, but I don't think it's enough. And so I want to bring up, Nancy Leveson has this lovely book called Engineering a Safer World from 2011. And she argues that safety should be regarded as a control problem. It's not that we build a safe system and deploy it and then we're done, but we have to maintain the safety of the system in the face of disturbances, like any controller does. So what is the controller in this case? Well, she says it's actually a hierarchy of controllers. It might be the driver in a vehicle. It might be a safety monitor that's remote. We've learned that the so-called autonomous taxis in San Francisco, there's actually a human being monitoring them. So they're not fully autonomous. There's, of course, the update team of system engineers who are responsible for making improvements and fixing bugs. And then there are the government regulators and so on, all the way up to the prime minister and so on. All these organizations have some responsibility for maintaining the safety of the infrastructure, the vehicles, and so on. Well, what are the disturbances? Well, she says the biggest disturbance to these systems is budget cuts and staff reductions. Particularly if the safety engineers have done their job very well, then there are no failures for long periods of time. You run for months, and there are no crashes or anything. And the company folks or whatever say, why am I keeping all these safety engineers on my staff? They're expensive and they're very talented. And I want to move them over to work on railway safety instead, or something like this, right? And so people are brought off. Less experienced people are brought onto the project, and she has some very painful, stories looking at, for instance, all of these kinds of decisions that were made that led ultimately to the Bhopal disaster. And, some poor engineer on the factory makes a mistake that leads to a catastrophe, and they get all the blame. But really, she says, over time, organizations tend to migrate toward the edges of safety because of these other factors: budget cuts, staff turnover, and so on. So, of course, there is another kind of disturbance. I'm not sure I have a solution to that one, right? This is a socio-technical problem. But there is a technical problem, which is that the operating environment may change because there are these unknown unknowns, novel or unanticipated hazards that could arise. And this is the other thing that controllers need to respond to. And I really like the work of a guy named David Woods, who comes out of the human factors literature. He's at Ohio State University. And one of his claims is that we have never built an automated system that could deal with novelty. There was always the human organization that brought the adaptive capacity to the system. Now, as an AI person, I sort of take that as a challenge. I mean, machine learning is supposed to be about adaptation. So could we do this? Well, I'm a little nervous about claiming we can do it, but maybe we can build some tools to help the people do a better job of it. So in particular, I've been very interested in detecting novel failure modes and novel objects. So there's a literature that was developed in 1980s and 1990s on what were called high reliability organizations that were studied by the people in management to understand organizations that do manage to attain high degrees of reliability and safety. And what they found in those organizations was that they had a deep belief that there were unknown failure modes in their system, and that their job as safety operators and engineers was to try to discover what those failure modes are before they happen. And their key performance indicators are things like, how many anomalies have we detected this week? How many near misses did we see this week? And if those numbers are getting too small, it means we're not looking hard enough. We should be looking for those things. And you see often in these failure stories, postmortems, there have been lots of near misses. I mean, we had this mid-air collision in Washington, D.C. 2 weeks ago, and now we read these stories. There have been many, many near misses. Because they're actually reportable incidents in aviation in the United States. But evidently they were just being ignored and not being viewed as a sign of a potential catastrophe. So what is the status of AI methods for detecting anomalies and near misses? Well, there's quite a bit of work in computer vision, and I co-authored a review article in Proceedings of the IEEE on anomaly detection, we said both deep and shallow, and I've done some work also with my student Alex Geyer. I think it's safe to say, or fair to say, that there have been a lot of advances in deep learning, in particular foundation models for computer vision, that have produced major improvements in our ability to detect novelty and unknown novel classes of objects, novel imaging conditions, and things like this. At the same time, no method can guarantee to detect all novelty. For one thing, you have to have a sensor that can sense the novelty, and if you don't have sensors pointing at the novel thing, you won't see it. There was an incident right in San Francisco where a cruise automated or semi-automated vehicle dragged a pedestrian under it that got trapped under the vehicle. They had no camera under the vehicle, so they couldn't detect that was happening. They hadn't anticipated that. So that would be very difficult to detect if you don't have the right sensors. An interesting side thing, there's a company in Peru called Artificio that is collecting road scenes from Peru to use to test North American things. And I think India could get into that business too. So they show lots of things that you wouldn't expect to see in North America. Okay, so in addition to these kind of perception failures, we could also have control failures. And I'm kind of running late, so I think I will skip over this a bit. This is my own work, so if we, I should be over here. Too many things to okay, so yeah, I guess the part I'm skipping over basically argues that particularly when we train computer vision systems with supervised learning, their deep learning is basically lazy. It will only learn to represent the things that it's forced to learn by the data. And so if the data does not exhibit variation in some important direction, the system will be blind to it, will not be able to detect it. So for example, if you only train your system on monochrome images, and then you show it something that is red, a color image, it will represent it as a grayscale image, right? Because it hasn't, it's sort of like principal component analysis. It hasn't seen any variation along some direction in the space, so it won't have a representation for that. And so if you, in traditional open category work that's been done in computer vision, we would usually only train on a small number of categories, and we would hold out some categories. But I think the lesson is really to take a foundation model approach, train on as much variation as you can find, inject artificially even more variation, generate synthetic data to try to get even more variation, because that forces the deep learning system to represent the world in its full glory and complexity. And so then when something new comes up, like say a one wheel, so this was is a little sort of motorized skateboard that did not exist when the ImageNet collection was made, but now it's marketed. And people who are riding on it behave a little differently than people that are on bicycles or skateboards, right? And so the computer vision system should say, oh, somebody's riding on something I've never seen before. I better collect data on it and add it to my classifier. So, so that's anomalies, and I think that we kind of have a handle on how to detect anomalies. But what about near misses? I think there are two cases here. One case is for the known hazards, right? During the design process, we identify hazards. We usually then introduce these safety margins, and we build detectors so that if we know the system enters one of these unsafe regions, it's a reportable incident. We know the aircraft came too close together. That's a near miss. So that's the easy case. The hard one, I think, is the counterfactual near misses. And so imagine, right, that our automated vehicle has a condition that it should maintain 2 meters of separation between the vehicle and all pedestrians, cyclists, and stationary obstacles. I mean, maybe in Bangalore it's 10 centimeters, I don't know, but there's some separation that's required. So now imagine a pedestrian is crossing the street in the crosswalk, and this automated vehicle with its LiDAR spinning on top is coming toward him, and he's not sure that the vehicle sees him. And he's pretty convinced it doesn't see him, and so he runs out of the way. The vehicle comes by and says, I had my 2 meter separation. It's not a near miss. But it's really counterfactual. If the pedestrian had not taken evasive action, there would have been a collision. And so the system needs to reason about whether it is causing the other vehicles around it and the pedestrians to take evasive action, in which case those should be near misses also. Now, fortunately, Judea-Pearl has this now very mature theory of causality that allows us to formalize counterfactual near misses. So I think this is an area, I don't know of any published work on it, but I think it would make a great dissertation for someone. In AI, of course, we've been working on diagnosis and repair of systems for 30 years. And so I think, or maybe even more, 40 years. I think the diagnostic reasoning of trying to figure out, well, given this problem, which parts of the system need to be changed is something that we could solve. And then the repair, at least for the machine learning system, is often adding more training data. For the planner, maybe it's adding a new hazard region, and so on. So I think we could do these things, or at least provide tools for humans to do these. But even that is maybe not enough. I'd like to just put one more idea out here, which is an observation that comes out of the David Woods in particular, but also Doyle and Carson at Caltech. They talk about engineered systems as exhibiting this paradoxical behavior of being robust and yet fragile. Our engineered systems are robust to the known hazards. We've designed the system so that it avoids all the known hazards with very high probability. But unfortunately, it can be vulnerable to these novel failure modes, to the unknown hazards. And part of the reason for that, there's this theory of what's called highly optimized tolerances, which I think is captured in this, which is that, subject to avoiding the known hazards, we then typically optimize our systems for power, weight, cost, and so on. And when we do this optimization, it pushes our design toward the edge of the feasible region, right? And so this is a cartoon, but imagine that circle is now the design space, and our design is right against the edge of the feasible region, and unfortunately, right outside of there is an unknown hazard, so that a small disturbance to the system could lead us into that hazard. So what can we do about this? I mean, partly maybe, some people say, well, we just shouldn't optimize very aggressively. And maybe it's true that regularizing, putting in factors of safety in all directions can help. But David Woods thinks that we need to improve the abilities of the systems to adapt. And he's usually thinking about the human system. So he's been doing a lot of work with the large cloud providers, particularly Amazon. He says, you think about a company like Amazon and their cloud system, they have the world's best reliability engineers working for them. And yet the Amazon cloud still suffers 24-hour outages over all of Europe, or it's just amazing that this extremely carefully designed system still has these massive failures. And often he finds that the different parts of the organization, of the company, have different views on what's going on inside this complex system. And if they could bring all those views together, they would be able to see what's going on. But unfortunately, because of the structure of the organization, they don't. Those of us in software engineering often talk about how companies ship their org charts, that the software system is decomposed along the lines of the organization that builds it. And so the sensors that are stuck into the system to detect problems, some for one organization and some for another organization. So he encourages organizations to practice horizontal communication so that they can compare notes during system operations. But I guess as an AI person, what I think about is how could we think about the design process we can think of as following some path through a design space, right, that takes us to some initial design. And I did some work in engineering design early in my career where the focus was all about trying to capture design rationale so that when something went wrong later, the engineers could come back and understand why we made the design decisions we made. But that was still, I think, too much of a build it and ship it mentality. And instead, I'd like to advocate that we build design tools that are available 24/7, 365. They're always on standby so that we have the entire design sort of hot, and if we need to make a change to the design, we could immediately move around in that design space to a new position in it. And that's how we could create more resilient organization. Okay, so in summary, I talked about machine learning trying to fit into traditional safety engineering, and I think the combination of high-fidelity simulation, risk-driven generation of training data and test cases, and then verification methods for trying to ensure distribution-independent generalization, that these would give us tools where machine learning could be made safe for safety engineering. But then I think we have to take seriously the message from Nancy Levison, which is that that the system has to be actively maintained, the safety of the system has to be actively maintained. And in addition to trying to defend it against budget cuts and staff turnover, we need to be trying to detect anomalies and near misses, that the AI methods for anomaly detection are reasonably mature, but that we need a lot of work on near miss detection, particularly these counterfactual near misses, which I think is a big hole in our toolkit. And then with these, I think we can also bring to bear some of our experience in diagnosis and repair. And then if we can build design tools that are always kept on standby, we can build organizations that can be able to adapt very quickly when they discover new failure modes. So I'll stop there and answer questions, and I'll make the slides available. I have all my references here.
Thank you for another talk. So on that last point about points to adapt, what would the trigger be? What do you have in mind for the trigger to actually, you said you keep the options hot, but when would you invoke?
Well, so I guess the hope is that when we see these anomalies and near misses, we try to diagnose, well, what caused that near miss or that anomaly? And then that may lead us to say, oh, we need to add a camera under the vehicle, or we need to make this change in our controller, or something like this. So the hope is that, that we could drive our diagnosis from the repair, as opposed to the outage. I mean, if we do have the failure of the system, then we're going to have to diagnose the failure, and then change our controllers based on that. But the hope is that we can detect it before the catastrophe strikes.
One of the issues that we face regularly is whenever we want to use simulation as the basis for doing what we are doing, that becomes a barrier for getting the system certified.
Yes.
So what any thoughts on how to overcome this mindset?
Well, one thing I've seen is that, at least for highway driving, we can think about test tracks also, right? So there's been some work. There's a private company that offers a closed test track near Berkeley in California, and the Berkeley team has published papers on deciding, out of all of the scenarios that we've simulated, which ones should we actually enact in the real world and check that our simulator works. And so in this test track, they have robotically controlled dummy pedestrians, other vehicles, and so on, so they can reproduce in a reproducible way, generate some real world scenarios. Now, it's not the same as real data, right, in some sense, but it's better than simulation. So you can also use that to do some validation of the simulators. But I mean, we can't go out and say, well, we need to kill 500 people in order to validate the design. That's not possible.
So how to educate the independent safety assessors about these things, you know? I mean, we understand, we learn that we can do it. But our safety assessors may not be aware of these developments.
Right. I mean, yeah, I think it would be, maybe we can do some work showing that that we could compare how well our automated methods for trying to find these worst case scenarios work compared to say humans trying to find those worst case scenarios, and show that our automated, risk driven sampling is more effective than human engineers. Do you need something here?
Thank you.
But I agree it's a difficult challenge to do, and yeah.
So we are a startup on railway safety system.
Mm-hmm.
So we have been working to deploy AI for railway safety system. Did you come across any use cases AI applied for railway safety systems?
I'm sorry, what kind of safety system?
Railway safety. Railway safety.
Railway safety, right, yes. I don't know of any. I mean, the U.S. railways are very far behind almost all the others in the world. So, I don't know of anything.
And to Waymo, which
right.
in San Francisco,
Yeah.
did you say this was a machine learning system for the safety critical application?
They're using machine learning in their computer vision, and I believe also in their planning for the trajectory planning. But they evidently it's not, they don't trust it to run fully autonomously, so they have remote operators who are watching them. And I think the vehicles, when they get into trouble, they just stop and wait for the human monitor to step in and get them out of trouble. There are lots of fun stories online of Waymo vehicles all stuck in creating their own traffic jam. Things like
It
this.
is also certified by TUV node. IMO system is certified by a third party TUV node. When they certify first at a standard. Did you come across any standard where machine learning applied for safety critical systems?
Well, there is this. Most of the work. There were some people on this panel from the German automotive industry, and they seem to have made the most progress on standards development. And they have this concept of safe for the intended application, right? Which they think they're going to be able to use to certify the machine learning components, where they. But I don't quite understand what that definition is, but it seems that it's narrowing things down to normal operating procedure, normal operating conditions maybe, and not worrying about the extreme cases. I'm not sure, but
We are the first company in India trying to use AI for railway safety.
right?
Let's see what happens.
Yes. Well, yes. May you be very successful.
Thank you, Professor. It was a nice talk. So I wanted to ask, so this was like very specific to like automotive driving and all. So what do you think about framework like this extending to other domains where ML is applied? So maybe like medical imaging and all, because there also it's very relevant.
Right.
I was also trying to think how this could be extended, if you could share.
Right, because I'm thinking maybe in medical imaging or in say robotic surgery. What kind of scenario?
So something like generally like how we deal with it, like we do some kind of segmentation and all. So there, how would we design like ODD space of where it is actually where we can use it and so on, because it depends a lot on the acquisition or whatever MRI we are using.
Right.
So it seemed, at least I was trying to think maybe it's slightly non-trivial.
Yeah. So I to be honest, I just haven't thought about it very much. The whole challenge of building a simulator for say cancerous organs or something like this seems very challenging. We don't have physics to help us, and so the range of possible variability seems huge. So so I don't know. Our report had a section on medical, but it was pretty weak compared to the discussion of aeronautics and automobiles. So I'm sorry. But I think it's you're asking very important questions. Yeah.
What are your thoughts on synthetic data for foundation models? We have seen traditional ML systems, that say if you can do object recognition very well, but if you put it on surveillance cameras, just doing downsampling of the image, you get great results. But once you do the real data from the real world, right, the results are nowhere comparable. So synthetic data normally is not a proxy for the real world. What are your thoughts? Like, do foundation models scale with synthetic data?
Well, I guess I was thinking about trying to generate synthetic novelty to force the representation to be good. But then on top of that, once you have that representation, then you're going to have to build your detectors, classifiers, maybe predictive models, and you'll need to get supervised data for that, I think. So I would be very worried about using synthetic data to train that part of the system. But more, I was worried that traditionally we just collected data, from the surveillance cameras, and then we just tried to train the models on that. And there's not enough variability in that data to capture the new cases where something novel happens. And so that's where I think a sort of foundation model approach that says, let's focus on learning a really good representation that can see everything that could possibly happen, quote unquote, and then build our system on top of that representation, maybe using supervised techniques or some mix of semi-supervised. I don't know. Yes.
The simulators that Waymo use, are there in the public, or they're like customly done?
I don't think they're public. They have published some data sets, In fact, they've published probably the largest driving data set. But I don't think anybody's made their simulators
So
public.
isn't the biggest bottleneck, like for RL, again, for building a safety critical system, is building
A high-fidelity simulator, yes. I mean, you've probably heard of Carla, which is a pretty good simulator for driving, but I'm sure it's not industry strength. And my colleagues are working on humanoid robot behavior, which they train entirely in simulation using this technique of domain randomization, right, where you train the controller for a lot of different worlds with different frictions and different robot masses and so on. And then they're able to transfer that to the real robot successfully. So maybe we need something similar in these other applications where we introduce more variation in the training process. But they're doing reinforcement learning. It's a little easier there, I guess.
Sim to DL is not hard anymore with modern techniques like domain randomization.
Well, they're having big success with sim to real. I'm a little surprised myself, but yeah, I don't know. I mean, a lot of the other robot groups are doing a lot of teleoperation data collection, right? Instead, so they have these very complicated teleoperation things where they can walk around behind the robot controlling everything it does, and then they try to do imitation learning from that. I don't know that that's very robust either, but then they have to generalize from that too. But okay, we should probably take this offline. Sorry.
Okay.
Yeah.
So please join me in thanking all for appreciation. Here is a gift kit.
Well, thank you.
Just books about
Wow. Yes.